Okay, so here we have on the weekend, we have concept check 3, and we're dealing with assembly language programming, although some of the stuff we've talked about in class has been had to do with subroutines and recursion. Those programs are sort of will be due at the end of this week, but the next week is the last week when we do pure assembly language. And so on April 8th, we'll start using dealing with C programming, which means we'll have to use VeraVirtual because we'll be using the C compiler and assembler, and those only run on Unix or Linux. Okay. And the problem is that we have to use also the simulator that's on Unix, because the assembly code produced by the C assembler, due to some weird way that the online simulator has been written, you can't run the LC3 assembly language from the C assembler on the online simulator. So we're totally restricted to using VeraVirtual for that part of the course. Okay, so here's concept check 3, which is, you can see assembly to binary, binary to assembly, assembler directives, symbol tables, complete the instruction, errors, different kinds of errors. A lot of these are like the puzzles. Spider has to do with strings. And then I've forgotten what this one does, but it's, again, I think something to like strings or some puzzle in programming. So that is where we're at schedule-wise. And so I can continue to sort of point ahead next week when you start working on the program on stacks. There's like 2 screenshots with different numbers. You should remember and look at the end of the instructions to make sure that when you have numbers to put in, like almost all the programs, you're supposed to take screenshots of them, but with particular numbers in the code, so I can see, because I know what the answers are supposed to be for that. Okay, so today, one thing I wanted to do at the beginning was, even though this is part of next week's stuff, is something you've seen all the way along, and might help you with one of the puzzles too, or understanding it, which is how does talking to peripheral devices work? And this is a snippet of code you can see up here that deals with input and output. And well, this one deals in particular with input. And that's it, because you can see here, there's 2 hardware registers here. One is keyboard status register, and the other is keyboard data register. Let's see if, okay. So these are particular addresses, right? XFE00 is the keyboard status register, and XFE02 is the keyboard data register. And those are fixed, those aren't memory cells. Those are, if you write a byte to this cell, it is, well, this first one might be a memory cell, but the second one is, it comes from the keyboard. And so instead of being a memory cell, it's whatever there's nothing in there unless you type at the keyboard. And so how does input work? Well, there's 2 ways of getting input from a slow device like a keyboard. One is by interrupts, where the device sets a signal hardware-wise, and the program then periodically checks that signal and then will respond. And that's what happens. But the online simulator doesn't implement interrupts, and so we're just to ignore that. And the other scheme is polling. That's why there should be polling. I'm not sure why I didn't put a G on the end. It should be polling, because you poll. That is, you request. You see here, this is A. This is what the program does, is it loads into R1A. which is the status register. Now, the status register is the first line loads the keyboard status register. Only the bit 16, the sign bit, is relevant because you see it says if the sign bit is 0 or positive. So if you look at the 16th bit, right, it's either positive or negative. It ignores, it only cares about this one bit here. So it's if this is a 1, you'll stop polling. But if it's a 0 or positive, then it just goes and loads R1. It's like an infinite loop. It keeps going. But then when you type something, what's going to happen is that this bit will be set to a 1 and it'll stop polling, because you don't want to run this other code until you've typed something. So this is when you call, this is part of the system call routine that will get a keyboard. So if the system call get C will have something like this in it, in which once you call get C, the computer's just continually polling the status register, waiting for you to press a key. And once you do, the keyboard sets the sign, the NZP, to be negative. So it stops polling and goes on and loads into R0B, which is the keyboard data register. Okay. And then this snippet here, this is not usually here. This is replace this with an actual task. For example, you might replace this with RET. If this was a subroutine and you're returning to the main program, that's probably what getC does, something like that. It's something like that because getC will save registers 1 and then reload the old register 1, so that if your program uses register 1, this subroutine won't affect it. So that's a general case when you have a subroutine that uses registers. You want it to save the registers it uses, then restore them to the old values so it doesn't step on the toes of the program calling it. So this is how keyboard input works, in which, for example, this you could do more stuff, like you could put in here out, in which it would print this character. Okay, but the point of this is that you can run this code as a full program. Maybe you want to put it in, you want to do JSR polling, and then change the, and then if you just leave it like this, it will be an infinite loop. So it enables you to practice keyboard input. And I don't know if this is accurate anymore. I have to check that. Okay, but keyboard output, see, you have a display register. They're the keyboards after this one, the memory cells, FE02, FE04. This is the display status register, the display data register, and it works in the same way. Here, okay, this is polling in, sorry about that, and this is polling out. It's not polling with, okay, whatever. So again, it continuously loads the status register for the display. Supposing the display was a slow device, and so it continually polls that until the display has printed its character, come back and says, oh, I'm ready for another character, in which it sets this one, its status register, to negative. So it stops the infinite loop here. And then this one stores, why? This is LDI, right? So yeah, because it's LDI because you're going and loading what's in this memory cell. And here you're storing indirectly what's in R0 not into location B, overriding this, but into FE06. So what this does is this takes what's in R0 and puts it in this memory cell. And when it does that, the display will print the character to the screen. And this is what out does. This is basic input output. Okay. Now this is an infinite loop. So the exercise for this was to combine these two code snippets to produce a program which implements keyboard echo. When you put these two programs together, so you have to modify this one here, like jump. You put these two together, like you might put these together in one program with say a JSR to this one, or just put a .org, right? And then change this number here to jump to this one, or put it or maybe you want to put it in a loop so that you will have a loop up here. So it basically does this. So it takes something in, prints it out, goes back and gets another one. So that's what's going here. Combine these two programs in a big loop. One can do this by replacing the first instruction here with the code from the second. You could actually just take this entire code here and stick it in here. And then that will, because then this one, and then you have to replace BR NZP poll out, so that if you put this code in the first one, then this one you can change this from poll out to poll in. So it does both of them in an infinite loop. Okay, one last comment in case you're working ahead. You have to be careful when writing this worm, because you want to make sure that, for example, let's say you want to make sure that, like here, let's say your program's here and it's going to have more than 4 lines, but let's say it has 4 lines. And then what it's going to do is copy these 4 lines down to 3. So you're going to have sort of the copies down here. And the last line of the program has to go and start this one running. Okay, so then this program runs and it copies another 4 versions down here, and then this one will start this one running. One mistake that what I don't want you to do is have this program copy itself down here, then run itself again and copy this one down here. So it just copies itself to memory, but you're always just running the first program. You want the first program to both copy itself and start the second program running, and the copy should copy itself to a third copy and then start the third copy running. Okay, we'll repeat this next week, but that's it for these 8 assembly language programs. And okay.